Electromagnetic radiation. Electromagnetic radiation is emitted by accelerating charges. The rate at which energy is emitted from an accelerating charge that has charge q and acceleration a is given by dE dt equals q square a square over 6 pi epsilon 0 c cube. So q is charge, a is acceleration, c is the speed of light. Part A, verify that this equation is dimensionally correct. So let's start with the dimension check for this equation. The rate of energy flow, dE dt, is suggested to be q square, acceleration square, 6 pi epsilon 0 c cube. Okay, so I'm going to check the dimension of this. So we're looking at the dimension of this equation, q square a square over 6 pi epsilon 0 c cube. We should obtain the dimension of energy per unit time, dE dt. Okay. So when I do this dimensional analysis, let me check about these quantities here. Acceleration in SI units is measured as meter per second square. So it is length divided by time squared. The charge Q is measured in coulombs. It's a fundamental unit. The speed of light C is in meters per second, which is length per unit time. The capacitance C is, for a parallel plate capacitor, epsilon 0, area of one of the plates divided by the distance, the gap distance between the plates, and the charge stored on the capacitor is the voltage multiplied by the capacitance, and that's voltage times epsilon 0 A over D. So now you can see from this one, epsilon 0 should be measured in coulombs per voltmeter. So this is meter square over meter, that's meter, voltmeter, coulomb. So epsilon 0 is permittivity of free space, can be written as coulomb per voltmeter, SI unit. And volt is basically joules per coulombs. That's the electric potential, energy per unit charge by definition, joules per coulombs. So I can see that the unit of epsilon 0 can be written also as coulomb square divided by joule meters. Okay, so having performed this exercise here, for the dimension of q square, I will substitute the fundamental unit, fundamental quantity, capital Q squared. For the dimension of acceleration squared, acceleration is meters per second squared. If I take the square, it's L squared divided by the time t to the power fourth, fundamental unit. For the dimension of 1 over epsilon, it's joule meters over coulomb squared. That means I have the dimension of energy times length divided by q squared. So that's what I obtain from this unit for 1 over epsilon 0. And then I have 1 over c cube. C is meters per second, so length over time. 1 over c is time over length, so time over length cube. So t cube over l cube. So let's see what happens here. Q squares will cancel. You can see the L square times L cube cancels the L cube at the bottom. Then I have T cube, getting rid of this T to the fourth, making it T. The end result is dimension of energy divided by time, which is basically what we are looking for. DEDT, dimension of energy divided by time. Okay, so that answers part A of the question. Part B, if a proton with a kinetic energy of 6 mega electron volts is traveling in a particle accelerator in a circular orbit of radius 0.75 meters, what fraction of its energy does it radiate per second? Okay, so we have a proton. Proton has charge 1.6 10 to minus 19 coulombs. It has a mass 1.67 10 to minus 27 kilograms. It's given that it has a kinetic energy of 6 mega electron volts, 6 times 10 to 6 electron volts, and the radius of the circular orbit is 0.750 meters. Now it's performing circular motion. That means its acceleration is centripetal acceleration, which is v squared over r, speed squared divided by the radius, and 1 over 2 mass of the proton v squared is its kinetic energy, Ek. So this tells us that v squared is twice its kinetic energy divided by the mass of the proton. Okay, so for the acceleration here, I can substitute this for v squared. I will obtain acceleration is equal to twice the kinetic energy divided by so it's twice the kinetic energy divided by mass of the proton times the radius of the orbit. So that tells me that the rate at which energy is emitted, DEDT, electromagnetic radiation, is q square a square, which means it is q square times 4 times its kinetic energy squared divided by 6 pi epsilon 0, 6 pi epsilon 0 c cube, and I will have, basically I'm substituting for a squared here, so 4ek squared, mass squared, radius squared, so mass of the proton squared, radius squared. So that's how I calculate the rate at which energy is emitted. And I also note here the value of epsilon 0 is 8.85 times 10 to minus 12 coulomb square divided by joule meter. Okay. So if I substitute these numbers for dE dt, dE dt is equal to 1.6 10 to minus 19 coulombs squared times 4 kinetic energy squared, 6 times 10 to 6 electron volts. Converting it to joules, I have to multiply it with electron charge, 1.6 10 to minus 19 squared. Then this is divided by 6 pi epsilon 0, 8.85 times 10 to minus 12, speed of light 3 times 10 to 8 cube, mass of the proton squared 1.67 10 to minus 27 squared, and then I have the radius squared, which is 0.75 squared. All right, so when I do this calculation, I obtain 1.33 times 10 to minus 23 joules per second, which can also be written, if I divide it by the electron charge here, 8.32 times 10 to minus 5 electron volts per second. Okay, so the problem was, what fraction of its energy does it radiate per second? So dE dt, the rate of energy flow, divided by its kinetic energy, E, which is now 8.32 times 10 to minus 5 electron volts per second, divided by 6 times 10 to 6 mega electron volts, 10 to 6 electron volts. This gives us 1.39 times 10 to minus 11. That's the fraction of its energy radiated per second. Okay, let's move on to part C of the problem. Now consider an electron orbiting with the same speed and radius. What fraction of its energy does it radiate per second? Now we're going from proton to electron. Mass of the electron is rest mass 9.11 10 to minus 31 kilograms. Mass of the proton was 1.67 times 10 to minus 27 kilograms. The acceleration, which is v square over r, is the same. So if I look at the energy, kinetic energy, it is 1 over 2 mass of the electron v squared. This is 1 over 2 mass of the proton v squared multiplied by the ratio mass of the electron to mass of the proton. Okay, so this ratio is important. What is the mass of the electron to mass of the proton ratio? It is 9.11 10 to minus 31 kilograms divided by 1.67 10 to minus 27. The ratio is 5.45 times 10 to minus 4. So The mass changes, but the speed and radius is the same. The speed and radius is the same. Therefore, acceleration is the same. So the charge is the same, acceleration is the same. V square over R is the same. However, the kinetic energy is 1/2 mv square. It's the kinetic energy of the proton multiplied by mass of the electron over mass of the proton. So we can see that dE dt is proportional to kinetic energy squared. So that's the answer we have found here, divided by mass squared. Kinetic energy is squared divided by mass squared. And that is 1/2 mv squared divided by mass squared, which means it's independent of m. So this tells us that dE dt doesn't change. The rate of energy flow doesn't change if it's an electron or a proton. However, if I calculate the kinetic energy, it is the original kinetic energy of the proton multiplied by the ratio of the two masses. So ratio of the two masses is 5.45 10 to minus 4. The kinetic energy of the proton was 6 times 10 to 6 electron volts. This gives us 3.273 kilo electron volts. So as for the fraction, dE dt divided by E, dE dt divided by E, we have the same dE dt, 8.32 10 to minus 5 electron volts, but 3,273 electron volts for the energy of the electron. The fraction is 2.54 times 10 to minus 8. Okay, so that's the fraction of its energy radiated per second if it's an electron. So you can see it's a greater portion of its energy if it's an electron compared to a proton. So in this part of the problem, for this problem, we have looked at first the dimensional analysis of this quantity, q square a square over 6 pi epsilon 0 c cube. Here, fundamental units are coulombs, meters per second. So q is a fundamental quantity. L over T, L and T are fundamental quantities. And I found out that epsilon 0 has the dimension of energy in its unit, coulomb square over joule meter. How did I do that? I looked at the capacitance of a parallel plate capacitor and recalled that the charge store is voltage across the two plates multiplied by capacitance, which gives me the unit of epsilon 0 of coulomb per voltmeter, and volt is joules per coulombs, so that's coulomb square over joule meter. So substituting that for epsilon 0 and for c, meters per second, acceleration meters per second square, L over T square, and for charge q, I obtain the correct dimension. Now, if I have a proton here with a certain kinetic energy on a circular orbit where the acceleration is the centripetal acceleration v square over r, I see that 1/2 mv square is the kinetic energy, so v square is 2 ek over mp. So 2 ek over mpr is the acceleration, centripetal acceleration. Substituted into this dE dt equation, I find this result. So if I calculate this dE dt and divide it by the kinetic energy of the proton, by converting the result to electron volts per second, I find the fraction 1.39 10 to minus 11. If it's an electron, the dE dt doesn't change. You can see that here, if it has the same acceleration, same speed and radius, same charge, the speed of light doesn't change. Epsilon 0 is constant. So this answer doesn't change. But electron orbiting with the same speed and radius, its energy changes because the energy of the proton was 1/2 mpv square. The energy of the electron is 1/2 mev squared. So I have to multiply it by the ratio of mass of the electron to mass of the proton. So that new energy is 3.273 kilo electron volts. So dividing the dE dt with E, the new value, I find 2.54 10 to minus 8, a greater fraction of its energy is radiated per second when it's an electron compared to a proton.